So in recent years, and even not so recent years, I've worked on atmospheric characterization of transiting exoplanets, but I have a long-standing interest in the velocity of the sun as a star. So in this talk, I'm gonna go back to my first love, and I'm gonna talk about line profile changes over the solar cycle. And I wanna acknowledge my ongoing collaboration with Joe Lama at Lowell and Guanwei Fu at Johns Hopkins, and I wanna thank NASA for research support. So what I'm going to talk about, well, first, I don't need to convince you that we need to study the sun in order to learn how to separate activity effects from center of mass effects in radial velocity. So the two main topics that I'm going to talk about today is I'm going to talk about variations in line profiles over a solar cycle, and I'm going to inject a signal into line bisectors and try to recover an Earth-like signal. And the data that I'm going to use for that is SOLAS. SOLAS stands for the Synoptic Optical Long-Term Investigation of the Sun. It's sponsored by the National Science Foundation, and it's run by the National Solar Observatory. And SOLAS obtains whole disk magnetograms and images in certain key lines. And they also do integrated sun spectroscopy in about 10 bands, in 10 wavelength bands. Each wavelength band spans about a nanometer at a spectral resolving power of about 300,000, which is very suitable for line bisector measurements. The downside of SOLAS is there's no absolute wavelength scale. They have some spectra that are taken with an iodine cell, but most of the spectra, they shift them so that they agree in wavelength with a high resolution Fourier transform spectrum, so that when I get the spectra, when I download the spectra, they are effectively in the heliocentric reference frame. So nevertheless, even without wavelength calibration, they are high quality measurements of line shapes. So that's what I'm going to study. There have been some published studies of those line shapes, very preliminary studies in 2014. So in this figure, I've overplotted. So for a while, SOLAS and HARPS North were both observing the sun on the same days. And I literally picked a random day when they were both observing the sun, and I've overplotted the spectra. If I shifted the SOLAS spectrum down a few percent, if I didn't do that, it'd be hard to see the difference. They're generally excellent agreement between the two. The lower panel here expands the upper part of the spectrum near the continuum, and you can see in the SOLAS data how smooth it is. The SOLAS spectra are very smooth near the continuum. They have very high signal to noise. Signal to noise of a single SOLAS spectrum is about 6,000 to 1. They have higher signal to noise than the HARPS North spectra per exposure, but HARPS North has many more exposures and of course many more lines. So both of these data sets are tremendous resources for studying the spectrum of the sun as a star. The big advantage of SOLAS is that it ran over a full solar cycle. It started in 2006, and they paused operations in 2018. This figure shows the sunspot number as a function of time, and SOLAS covered all of cycle 24. They paused operation in 2018 when the facilities on the National Solar Observatories on Kitt Peak were decommissioned, and they are moving it to Big Bear. It has taken them longer than they would like, but Luke Bertello tells me that they will be restarting this year. And of course, HARPS North has been running, and Express is now running, and NUIT is running, so there will be a lot of facilities looking at the spectrum of the sun as a star. So I'm studying line bisectors, and this is the line bisector of a neutral iron line at 537.96 nanometers. And the bisector is plotted here on an expanded scale. And what I'm interested in knowing is, does that bisector vary over a magnetic cycle? The bisector has the classic C shape, which Dan Ostrava showed years ago is due to the asymmetry. The line asymmetry is due to near surface convection, where you have hot rising regions and cooler falling regions that produce this line asymmetry. And I'm particularly interested if we can recover small wavelength shifts in the bisector, even when the shape changes. So about 2 years ago, Andrew Collier Cameron and Eric Ford and their collaborators published a paper where they separated activity effects from center of mass effects in radial velocity using the autocorrelation of the cross-correlation function. And line-by-line studies have tremendous advantages for radial velocities. So I'm interested in doing the same thing, the same separation, on a line-by-line basis using line bisectors. So that's what I'm trying to do here. So what I do is I have, in the SOLAS data, I have about 23,000 bisectors. I pick out 8 strong lines in the SOLAS bandpasses, and I Fourier interpolate the spectra so that the process, the numerical process of measuring the bisector doesn't introduce any additional noise other than what's in the data. I inject a 9 centimeter per second radial velocity signal with a 1-year period. That's the Earth. Then I'm very fond of simple analyses. So I use a principal component analysis. On each individual line, I use a PCA, and I determine the principal components of that line bisector. And then for each individual line bisector, I fit those components to each individual bisector, including a shift, a 0-point shift in the wavelength, which would represent the center of mass radial velocity. And I'm going to see if I can recover my injected 9 centimeter per second signal. And I'm also going to examine how the span of the bisector changes over the solar cycle. I define the span of the bisector to be the wavelength in the line core minus the bluest part of the line bisector, converted to meters per second. So here's an iron line at 539.31 nanometers. The blue line is the absolute magnetic flux averaged over the disk from magnetograms. And I flipped it, it's upside down here. So the lowest part of the blue line is the most magnetic region, is the most magnetic part of the solar cycle. And it's not a fit to the data. I've just flipped it upside down and scaled it kind of arbitrarily to see if it has the same shape. And the bisectors here are averaged over 100 days. And you can see that over a solar cycle, they have pretty much the same variation as the average magnetic flux on the sun. Here's the manganese line at 539.5 nanometers. This line has a lot of hyperfine structure. And that hyperfine structure combined with its Zeeman sensitivity makes the width of the line profile much more sensitive to magnetic effects than other lines. It also shows a similar effect, but it looks like there's an offset in time between the data and the average magnetic flux. It may be that higher moments of the magnetic flux are more important, not just the average, but how that average is distributed across the solar disk. Also, you notice that the scatter, I've binned the bisectors here in 100-day averages, and the scatter is greater than the error bars, and I think that's due to microtellurics. This spectral region has very weak water vapor lines that I have not removed from the spectra. I've measured the bisectors just as is, and those microtellurics are probably affecting these line bisectors. Now, can I recover my 9 centimeters per second signal? I'm going to show you 3 lines. The good, the bad, and the ugly is what I call them. Here's the good line, or here's one of the good lines. There's more than one good one. But this is an ionized titanium line at 538.1 nanometers. The average bisector is about 50 meters per second. It has the classic C shape. And it can almost recover a 9 centimeters per second shift. And that's reasonable. There's thousands of bisectors. The signal to noise in a single spectrum is 6,000 to 1. This bisector is relatively well behaved. So the shape changes in the bisector are sufficiently benign that we can recover a shift 9 centimeters per second. Okay, but here's the bad and the ugly. So the bad line is a neutral iron line at 539.7 nanometers. And it just has, you can't recover the signal because the noise is very great. And the noise is great. And the bisector doesn't have a C shape, it's just a slant. The reason is that this is a blend, it's a known blend. I knew that. If you looked at it with a human eye, you wouldn't see the blend. But the atomic spectroscopist will tell us that there's another line blended there. And indeed, that affects the bisector. It makes it hard to recover that 9 centimeters per second shift. The ugly, I'm still working with this ugly line, but it has a perfectly good bisector. But if anything, it has an opposite effect than the 9 centimeter per second shift. And I think this is the effect of microtellurics. I do see seasonal effects in these bisectors, and I think this bisector, it's detecting an Earth-like planet, all right. It's detecting the one we live on, because the summers at Kitt Peak are more humid, and with this bisector, I'm not able to recover the 9 centimeter per second shift. Nevertheless, in the average of the 8 lines I've looked at, virtue is rewarded if I weight them by the inverse of the day-to-day variance. There is not whether they agree with the signal that I know is there that I injected, but whether they're consistent from day to day, and I use that variance as a weighting, the inverse of that variance as a weighting, then the average of those 8 lines recovers that 9 centimeters per second signal pretty well. So what I conclude from this is, first of all, the span of line bisectors changes with solar magnetism, as you would expect. It's during high magnetic activity on the sun, the size of the line bisector, the span of it is decreased by about 10 meters per second. And it's approximately proportional to the average magnetic flux. But there probably are higher moments that are important also. And there are telluric effects, seasonal telluric effects in the line bisectors. My PCA decomposition is able to find that 9 centimeters per second signal. But first of all, it's an injected signal. It's not a real signal. And real signals will be harder. There are other sources of false RVs besides changes in the line bisectors. See Steve Sarr's poster for one example of that. And stars will be more difficult, of course, because the Earth's orbit is almost circular. So the solar spectrum doesn't move very much with respect to the microtelluric background, which will be more difficult to remove and correct for stars. So what I want to do next is I'm starting to look at the HARPS North spectra and the NUID spectra and the express data that Joe will talk about shortly, and look at line bisectors to try to recover a real signal, the Earth-Sun radial velocity, to as high an accuracy as I can. And I'll stop there. Thank you.
All right, do you have any questions? Lily is easy one here at the front, so I'll give you the privilege of the first one.
I love that you've been to 100 days. That's like such a power move. Have you looked at if there are signals on shorter time scales? Would you say like the bisector only tracks the activity cycle, or even like rotation? You can see differences in the bisector.
So I didn't quite hear that real clearly, but you're asking if do I see rotation signals? I haven't looked for rotational effects. Right.
Thank you.
But I definitely see seasonal effects in the bisectors. The Kitt Peak is not a good place for a spectrometer. I'm sorry, NUID.
The other microphone was handed off, so you're lucky. Get your question in quick, and then the rest go on Slack, please.
Hello. Thanks for a great talk. I just had a question about your PCA over here. Do you find that your results vary depending on how many components that you need, or do you only need 2, one for the shape change and one for the center of mass?
I've experimented with that a little bit, and they're not terribly sensitive to the number of components I use, but I need to look into that in greater depth. I'll have a paper later this spring and summer that I'll go into that in greater depth, but I don't think it's very sensitive to that.
Thank you.
All right, let's thank our speaker again, and then we'll get our next one set up.